Tend to be the hardware than it is to change the software that was running on that old hardware. So agreeing on the ISA gets you lots of great software. So you get tools that know how to speak this language. So you get compilers, assemblers, you get tools that let you debug programs that are running on that kind of hardware. You can get visualizers that show you how the code is executing through a machine speaking that language. You get emulators of things that can pretend to be that hardware, and simulators that can simulate that hardware. And then you get all this great stuff like documentation and programmer's guides and application notes and things that you can find when you search on the internet and you go to Stack Overflow. There's actually answers there because people are using this ISA. So it's really important to understand that an ISA is just the standard. It's just what we agree on. It's not any sort of implementation. It's just the rules. But standards are really important. They make a huge difference in the hardware world. So for example, in networking, Ethernet and TCP/IP is an open standard. It's you just go online and you can see it, and you can implement your own version of it. And I had to do this in one of my grad school classes. I didn't do that great, but students learn how to do networking this way. And there's lots of proprietary implementations as well. Similarly for OS, there is a standard for how to do multi-threaded things, so you don't have to kind of understand what hardware you're writing on when you're what kind of hardware you'll be running on when you're writing your user-level application. And so the operating system kind of provides that abstraction. So Linux and FreeBSD are open implementations of this, but Microsoft Windows does the exact same thing, or uses the same standard. So you can write apps that are kind of portable across the two. And like we said, the C high-level language is also a standard. I think your head would kind of explode if somebody told you, oh, you can't write a C program, you don't have a license for C. It's an open standard, anybody can use it, and therefore there are free and open compilers, GCC and LLVM, but there's also proprietary implementations of those compilers. So for example, Intel has a compiler that will make sure that C code compiles really well to run on an x86 processor. And ARM does the same thing to make sure that their stuff runs really well on ARM processors. And they don't really want the other side to see the cool tricks that they're doing, so those are proprietary implementations. Similar with databases and graphics. But before, RISC-V has been around for a little while, but before RISC-V, there really wasn't an open standard. It was just the standard, just the rules that we're going to follow. And therefore, there weren't really any free and open implementations of this non-existent standard. But there were lots of proprietary standards, like x86 and ARM, and so there are lots of proprietary implementations. The problem with the proprietary ISAs is that they come and go. They're kind of subject to the whims of companies and their successes and failures and business decisions and stockholder pressures and things like that. So some of these things are before my time, and Intel is now kind of x86 shop. Before that, they had different processors, different ISAs. Those are all kind of gone and retired. If you had a program that worked on those, you can't run it anymore, or you have to have an emulator. Another great example is MIPS. So they have an ISA that the company built processors that use that ISA, and it was proprietary. The company got sold to Imagination, then they got by Wave, an AI startup, then they open sourced their thing a year ago, and it was really exciting. I just learned yesterday that that's not even open source anymore. They just killed it. So you're completely at the whims of companies. Similar story with Spark. They open sourced their they made their open Spark processor. Then the company got acquired by Oracle. They got shut down. There's still people making the processors, but it just kind of comes and goes. And even ARM is incredibly popular right now, but the company itself was sold to SoftBank, and now it's being sold off to Abu Dhabi Investment Fund. It's just never quite sure what might happen, what these different kind of investors might decide to do with ISA. So one other thing about why RISC-V, why is RISC-V coming? So if you look at a modern chip, which you might call an SoC or system on a chip, the question is, how many ISAs does it actually speak? This is a chip that comes from NVIDIA. So if you've been listening to my talk, you might think it speaks the NVIDIA ISA. But that would be a wrong assumption. Modern SoC is made up with lots of different processors, actually. There will be an applications processor, often ARM, which is kind of the workhorse, just kind of managing everybody else's tasks, doing all the general purpose stuff that's hard to generalize. But then there's graphics processors that are doing lots of like matrix operations and convolutions and stuff like that. Similar with image processors. Then there'll be like radio DSPs that need to do Fourier transforms and like just process a lot of data. And they don't need to do things like, just random memory accesses and stuff like that. Similar with audio. Then there'll be security processors that are optimized for doing like AES operations or like block encrypt operations. And they might be kind of hardened to make sure that they are resistant to attacks, which I think we'll talk after this one. And then there'll be like a power management processor that's super simple, super boring. You just want it to be small and work and not take up a lot of space. And each of these have their own ISA because they're all proprietary. Or why is it like that? So first of all, the ISAs don't work very well to each other. So the apps processor ISA kind of has to deal with everything kind of well. So it's big and inflexible. And the accelerator's like, I don't want to do all that stuff. I just want to do my Fourier transforms really well. And so the accelerators have to come up with their own language. And then secondly, all of these IPs are actually coming from different companies. I mean, NVIDIA is not an expert in making all of these things. Sorry. I've got my timer going. So NVIDIA is not an NVIDIA is not an expert in making all of these things. So they have to buy these things from different providers, and the different providers, don't have rights to each other's ISAs, so they all have to come up with their own languages. And then finally, there's some things that are like so simple, you might task someone in your own engineering staff to, build the processor for this thing. And, I'm a hardware designer. If someone comes to me and says, hey, I need you to build a processor for our chip, I'm not going to go buy someone else's because that's my job, so I got to come up with and design something, and so I have to make something up. And then, I have to make up my own tool chain and everything else. So that's how we sort of end up in this mess of all these different languages being spoken on a chip. So the question is really, do we actually need all these different ISAs? Do they really have to be proprietary? And do they have to keep vanishing? So what if there was one stable, free, open ISA that everybody could use for everything? And that's really the idea behind RISC-V. So in 2010, some Berkeley students, grad students, Andrew Waterman and Yunsuk Lee, the guys on the outside in this picture, were working with their professor, Krista Asanovic, and Dave Patterson of Hennessy and Patterson fame, if you ever had to take a computer architecture class. So their group is a computer architecture research group, and they're just trying to get their research done. They've got cool ideas they want to try out, and they need some a CPU to start with that they can modify and do their cool research stuff. But choosing that starting CPU was hard. It was like getting in the way of their actual research. So they had some options. They had the proprietary option of ARM or x86, but their licensing issues, they have to go to those vendors and say, hey, can I have your core and be able to modify it for research? And these companies don't generally allow that. And for companies that they do allow it for, like Apple, they just get paid like ridiculous amounts of money. And also, even if they were given permission, it's a very complex language. These things are kind of built up over time. They've got all kinds of stuff in there, and it's not just add and subtract. There's all kinds of crazy stuff. And it's too complex as a starting point if you want to kind of add on to it. So they looked also at open source options, but at the time there weren't very many, and they're kind of making a lot of assumptions about the implementation that they were going to use. So there might be an ISA that's very tightly coupled to the CPU that implements it, which is not exactly what you want if all you want to define is a standard that anybody can implement. So they were like, all right, well, it's summer. We don't have anything else to do. Let's do this 3-month project over the summer to just start from scratch with a clean slate ISA. And they called it RISC-V with the V because it represented the fifth major ISA coming out of Berkeley. So they've been kind of doing this stuff for years, and students would come and go. But RISC-V was going to kind of take everything that they'd learned and start from scratch. So RISC-V as an ISA is super boring. It goes back to basics. The intention was for it to be simple to learn and implement. So they want it to be a learning tool and then easy to implement so you can get onto your cool stuff that you actually want to do. But at its heart, it also makes it easy to add bells and whistles. So it's designed to be extensible. It's designed to be modular, so certain parts of it are defined, but like you can add and remove them as you see fit. And you can add your own custom stuff that you think of. And actually, it's so simple that if you go to the RISC-V website, for every instruction in the ISA, they actually trace the genealogy of the instruction back to like, the first computers or whatever that implemented it, and show that this is like, there's no new ideas here. It's just, we just picked all the stuff that we showed over years actually worked. But boring doesn't mean like slow or bad. It just means it's really easy to implement, which means you can like get on to the cool stuff and make it fast or add your custom stuff. So, they did this just for their own usage over the summer. So they were kind of doing it, and they had, their like internal website or whatever and some papers that were being published. And as they were doing it, they were making changes. And then people outside of Berkeley started complaining, which is kind of weird because this is just supposed to be for them. So it turned out that other people were finding it really useful to have this simple, boring, easily extensible ISA published, because as the Berkeley people were doing work and like working on the tool chains and everything, other people could use it. But then they start, if you change something, then you're like, wait a minute, my computer doesn't understand your code anymore. What happened? Oh, you guys changed the ISA. This is getting annoying. So they decided in May 2014 to actually freeze the user spec. So they decided, 4 years later, after the 3-month summer project started, they kind of had made enough learnings from all these tape outs and publications that they'd done along the way. They did a ton of Kirsty is super obsessed with how do the bits actually get lined up in the instruction to make sure they'll be really easy to decode. And so in May 2014, they actually said, this is frozen. We're not going to change it anymore because people care. And then they decided to do something additional, which is to create a separate foundation called the RISC-V Foundation to maintain the standard. Because, if it's at Berkeley, there's like grad students, they come and go, and people's, projects languish. But the foundation was created to kind of keep this living in perpetuity. So RISC-V is the open source hardware instruction set, and it's free and open to use. And the spec was ratified in 2014, and additional specs have been ratified since then by the foundation. So the foundation is it's a membership organization. Companies or individuals or other groups can join. So there are 13 university members. There are 29 research and consulting type organizations. There are organizations who joined who do software and tools development who want to run stuff on RISC-V. There are people who do like machine learning, and they want like custom hardware for that. And so there are companies that build, design chips. And then there are companies that actually build chips that like manufacture silicon wafer chips and things. And then there's also individual members. So anyone can join the foundation. It's free. You just have to like check off a thing that says you won't sue each other. And that's literally what it says. Yeah, and it's also a worldwide movement. So, Intel is an American company, and ARM is a British company. And other countries kind of like get a little grumpy when they have to just use other people's technology. So countries like India, the Indian government actually declared RISC-V the national ISA of the country. It's true. And the Chinese government is also like heavily investing in companies who say that they're going to do anything RISC-V, because they really want to like get out of the yoke of this licensing thing themselves for, national security reasons as well. So the RISC-V ecosystem, the foundation is really, just mandating the standard, maintaining the standard. So they have the ISA specification. It's on their website. There's repositories and things where people on GitHub, you can comment and file bugs and stuff like that. They also have golden models, so things that actually, show you how the code is supposed to execute. So you can run a program through it and be like, okay, is mine doing the right thing just based on this model? And then they also have compliance tests. So if you have something, you say, I think this thing is RISC-V compliant. I want the RISC-V sticker on it. They maintain the test suite to say, okay, yep, it's compliant. You can put the RISC-V logo on it. But underneath that, there's hardware. So there's open source hardware, tons of them. Pico RV32 is the one that you've got 2 of on your badge. Rocket is the one that I work with a lot. But then there's also commercial core providers. So people who sell RISC-V cores, that's also something that I do. And then there's also companies that develop cores in-house, and they don't really, they're doing them for their own purpose, maybe for those power management CPUs and stuff. But we know that they're on their chips. And on top of that, there's the whole open source software ecosystem and the commercial software ecosystem building up on top of this specification. All right, so just to remind it and really drill in the point, what is an ISA? It's just the standard. It's not the actual piece of silicon that can execute code. It's not the chip. It's not the tools and compilers that you need to generate the code that's going to run on the chip. It's not a spec for anything else on the chip. This is also important to note. If you have something you say is ISA, the ISA is RISC-V, it doesn't say anything about, yeah, but how do I actually make the LEDs blink? There's no blink LEDs instruction. So there's something about how do I map things to pins and memory mapped, or is there special custom instructions or what? And it's not all the OSs and drivers and software that are written to that standard. And just to finish up my example of ISAs, this is the add section of the RISC-V manual that's on the RISC-V website. And you can see it's very compact. They actually have a bunch of instructions, including add in this one little section. So RISC-V is really becoming the ISA of choice for education. If you ever taken a computer architecture class, you might have used one of these two books on the outside. And those have both been kind of switched over to teach RISC-V. And this is really cool because students are learning RISC-V, and then they can come into the industry and use RISC-V. So I know when I took computer architecture, I learned some sort of fake MIPS thing, maybe. And then when I came out and started, okay, now I have to write assembly code that's actually going to work, it was x86. And I was like, I don't know this at all. What is this? And so it's really exciting to have students coming and interviewing for jobs that are yeah, I know RISC-V, I did RISC-V. And it's just it's just going to make things so much more efficient for everyone. And in the middle is the RISC-V Reader, which is a book that was written by David Patterson and Andrew Waterman, which is a really great reference. It's a little bit longer and more verbose than the actual spec. So RISC-V is also becoming the ISA of choice for researchers. I made this very scientific graph by going to Google Scholar and Googling RISC-V over the years. Apparently you used to be able to do this with a bot, and they kind of killed it, so I had to do it manually. But yeah, I do remember the moment when I first got an email that's hey, you have a citation, and I saw RISC-V in the title, and I was like, yes, it's happening. So researchers are really starting to leverage the intention of RISC-V to make get the research done. And so one example of research, I don't know, I think this is kind of a hacker thing. So this team at MIT, they built an actual carbon nanotube microprocessor. This is the first time this has been done. In the past, people made a gate or maybe a few little gates together, but they actually made a working CPU. And it's actually RISC-V, which is so cool. It's half RISC-V because it's only 16 bits instead of 32 bits. But the point is that because of RISC-V, we can really focus on the cool part of your project. You don't have to sit around and be well, if we're going to design a CPU, what should the add instruction be? It's whatever, just go read the RISC-V manual and you just make the carbon nanotubes do their thing. So I think this is the real power of RISC-V, that it's not about the ISA, it's not a problem anymore. Just do something else. Pick that and move on. So, where do I come into all this? So I'm from Stanford, I'm not from Berkeley. So I kind of knew about this stuff. In 2016, I was working at a crypto hardware company, which was super cool, but super secretive, and nothing was open source. And I heard that the RISC-V inventors were starting a company to actually build RISC-V silicon. The company is called SiFive. And I had evaluated RISC-V for a project, but at the time we were kind of this is cool, academic thing, but it's not really ready yet. So I was cool, I can go work and help solve a problem that I'm facing in industry, this problem of picking what processor to use. And I get to do it through open source projects? Yes, please, let me. So I joined SiFive. And in that year, so the first year, we made the first commercially available RISC-V silicon. So people had taped out RISC-V chips before. A taped out a chip means you actually make a chip. But no one was selling them. So we actually made a chip that you could go on crowd supply and buy the board. And I think we're actually selling them on DigiKey now, the same guys. So that was in 2016. And then about a year and a half later, we did the first Linux-capable RISC-V multi-core chip. And so the question is, these are running RISC-V, so are these open source chips? And the answer is kinda. So free and open ISA does not imply open source hardware. but it allows people to make open source hardware implementations, or closed source, or a mixture. So the SiFive chips are actually, much of it is open source, but there's things on the chips that are proprietary IP, and so those parts aren't open sourced. And RISC-V ISA says, do whatever you want to do. It's fine. Just don't lie and say it's RISC-V when it's not. That's the only thing they'll come after you for. But I think RISC-V does give you the ability to build open source hardware that's practical. So now people can build open source cores and platforms. So again, the badge FPGA, the core that's on here is open source, and it's one of many, many RISC-V cores that are open source that you can find, written in lots of different languages. And then you can build a platform around that, like how do I blink LEDs once I have this RISC-V core. And you can use your open source compilers, and you can run open source OSs, and you can run a bunch of open source apps on top of those OSs. So this is one project that I did. I don't know if you can tell, but my shirt is glowing in this picture. But so basically, this started with the 32-bit embedded Rocket RISC-V core, which is open source. You can go see the stuff on GitHub. And we taped out that silicon that we talked about, and we open sourced as much of that as we could on this repo. And then we put that on the Hi-5 PCB, which is an Arduino form factor board, and we released all the schematics and everything. And then we ported Arduino runtime thing, and we called it Cinco. And we had that running on the board. And then I'm a big fan of the Adafruit stuff because it always just works. So I ported the NeoPixel library for this little matrix and got my thing to glow so that I could go to Maker Faire and hold my head up. And so I think it's really cool that I got to like touch all of this stuff, and we kind of moved things a little bit farther down or up in my picture from where we were before. Just some other examples. This is one from my coworker. He ported Zephyr OS to a similar next revision of that board, and he has all the open source demo for this. The video doesn't really work in here, but like it's a little pendulum demo. But really the point is he was able to port Zephyr OS and move that forward, RISC-V and Zephyr together. And then AB Open is a different company or different organization that took that Linux-capable board, a Linux-capable chip and a Linux-capable board and an open FPGA image from Microsemi, and they put it all together with this like really well done Linux from Western Digital, and they put it in a box, and now you have a RISC-V PC that actually you can definitely run like real apps and things. So the point of what point I'm trying to make is just because RISC-V doesn't require you to be open source, it definitely enables you to do a lot of open source stuff that you couldn't do before. So where do FPGAs come in? I'm just going to do a time check. Where do FPGAs come in? So, like, why do we care about having an open source core chip? I mean, the point is that you can look at it, you can read it, you can understand it, and then you can change it. Or you can throw it away. But let's say you change the code for a core, and then you say, cool, I changed it. I went to your website and I changed your code, and now I want a new chip. It's going to take weeks or months to build that chip, just the process of like slicing up silicon and like making little masks to shine light on the wafers and like chopping it up and polishing it. Like these are all the steps that go into actually building a chip. So that's going to take a long time. And that's assuming you actually know what you want to build. If you want to figure out what you're going to want to actually build, it's going to take months to years on top of that. So FPGAs totally solve this problem. So FPGA stands for Field Programmable Gate Array, and it's like this thing on your chip, the big guy. And what it does is it allows you to change the chip's hardware in a few minutes. So when you're loading programs onto this, and I'm sure someone will talk about this more in the workshops and everything, you can either load code onto it, that's like the program you want it to run, or you can actually load a program of what is this chip supposed to act like. So right now it's told that you're supposed to act like 2 RISC-V cores and a bunch of other awesome stuff, but you could go in there and you could change that. And I think there's workshops about that yesterday and today. So here are 5 ways to modify a RISC-V-based design that are like actually interesting now that you have an FPGA, because you don't have to sit around waiting for a chip to come back. So you could tune the CPU that's on there. So that means you could take the CPU, you could change things like the cache size, how much memory does it have, how much branch prediction does it do, how deep is the pipeline? So you're kind of trading off frequency and area to try to get something that works for your application. Maybe you need something that fits in this FPGA, that's a tiny FPGA, and all you needed to do is like blink an LED. Or you actually want to do some crazy, machine learning acceleration thing, and you need a lot more resources, and it fits on the FPGA, so you can change that stuff. I would say this is kind of basic computer architecture stuff. You don't really need a special ISA to do this. Like most ISAs will let you tune these sorts of things. Next thing you can do is tweak the CPU. So remember, part of the glory of having open source design is that you can actually look at it and understand it. So I was having a conversation with one of my mentors in grad school, and he mentioned like, oh yeah, I think there's a patent on multiplication by 0. Like if you multiply by 0, you can just not do it, and then like saves you some power. You just know the answer is 0. So I was like wondering, do people actually do that? Like forget the patent, just like, is that something computers actually do? So I Googled it, and somebody else asked the same question on Stack Overflow, and nobody really knew the answer. And this is a 7-year-old question, so I don't know. But the point is, we can go into the FPGA CPU file and figure this out. I don't know the answer. And the point is, it's a trade-off. You can decide what you want. So if you're like, I really want the best performance, I don't want to be multiplying when I don't have to, then you could change the code to make it do that optimization. Or if you're like a security researcher, this is like making all the alarm bells in your head go off. This is terrible. Like this is not constant time operation. This is going to have terrible side channel. So I'm going to go in there and make sure it always multiplies by 0. And so this is one of the reasons that RISC-V is really exciting for security community is they can get in and look at it and say, I don't have to do some crazy analysis to figure out if this is going to be susceptible to some of these Spectre and Meltdown attacks. I can just go look at the code, and then I can fix it to make sure it doesn't. Another thing we can do is customize the ISA. So like we said, the RISC-V ISA was designed from the ground up to be extensible and modular. So the base instruction set is the I instruction set, which is really not much more than add, subtract, load, and store, basically. And so even multiply is an extension, which you're like, isn't it definitely going to need to multiply? It's like, well, you can do that with adds. You just keep adding. If you want to do divide, you just keep subtracting. So if you really don't want to waste the area for a multiplier, you don't need to. Similar with F, it stands for floating point, which is a pretty expensive piece of hardware in any case. And if you're just that power CPU controller thing, you definitely don't need, I don't know, I've never designed one of these, but you probably definitely don't need floating points. So you're not going to waste area for that. And similar with the A and D and other extensions. So the idea is the hardware is modular, and therefore the compilers know that, and the compilers are modular. And then in addition to that, there's a bunch of other extensions which are kind of in flight that are using this sort of reserved space. And those are reserved for the RISC-V Foundation standardization extensions. But there's a separate part of the space which is especially designed for people to do whatever they want. It's like the foundation promises we will never use a space. It's only for custom extensions. So if you're a company and you're like, you know what, I have something that I think is really special and it's going to make my code on my hardware work really well. I want a custom extension and I'm going to put it in this custom space. That's fine. You are like allowed and encouraged to do that. So other companies have the concept of extensible ISAs, but often the extensions are sort of baked in and they're kind of part of the product. And it's in RISC-V, it's really in your control, like what makes sense to mix and match. So another big one is you can just replace the whole CPU. So if you get this FPGA and you're like, oh, that Pico RB32 is awesome, but I designed my own thing, or I saw this other thing, I want to see how that works in comparison, you just swap it out. And if everything's done right, the software should just work. Because that is the true power of RISC-V, is that you pick the ISA first, and then you pick the implementation. Before, you had to kind of decide, like, well, let me look at how much things cost, and then I'll figure out which company I'm going to talk to, and then they're going to kind of torture me once I try to like change to the next chip that I'm going to do. But now you're just like, no, I'm using RISC-V, and if I don't find what I need today, I'm going to go to somebody else. And if I still don't find what I need, I'll just design my own thing. Let's say I start designing my own thing, and I get about 2/3 of the way through, and I'm like, ooh, wow, like, how do interrupts and debug interact again? Oh, this is getting like tricky. then you're like, that's fine. Just go back and like look for alternatives, or go look at what other people have done and see if you can improve your implementation. But the point is, these things should be fairly interchangeable. You can also replace something that was like lower performance with something higher performance, to kind of have maintain the same platform. But as people are coming out with like more and more impressive RISC-V CPUs, you can kind of just keep moving up on the chain. And finally, you can modify the platform. So I know we're like very used to on these sorts of badges. I know there's a cartridge, so you can like add extra hardware on the board. But with FPGA, you can actually add extra hardware in the FPGA. So I've used a few projects that I saw when I was looking around. So I've always wanted to have an FPGA driving NeoPixels because I feel like the NeoPixel code is like overly complicated for what it actually is. And so somebody actually did this project called EasyPixel. As far as I can tell, this is not an open source project. Someone can correct me if I'm wrong. But you could go read the NeoPixel spec, design some hardware that does a NeoPixel thing, open source it. Other people can put it on their badge and reuse that thing. And another example is NVIDIA open sourced their NVDLA accelerator for machine learning. And SiFive actually has a demo where we take that open source thing and we add it to our open source Linux FPGA platform, and you kind of enhance the whole system. And all of this, you can do it in a few minutes with an FPGA. You don't have to like debug and debug. You just like try it and see if your NeoPixels blink or not. So RISC-V Foundation really recognizes the power of FPGAs, and they've started an annual contest based around FPGAs. So in 2018 was the first year that they did this, and the challenge is basically like, let's get as many people as possible to build RISC-V FPGAs cores. And so there were two challenges. One was the smallest possible RISC-V thing that was compliant to the spec, and then the next was the most performant that was able to fit on a given FPGA. And they had tons of people entering, lots of techniques, lots of languages that people use. People use different languages like Verilog, System Verilog, Chisel, Spinal HDL, and probably other things that I'm not aware of, System C, maybe, sorry if I'm not saying your favorite language. And the cool thing is that part of the requirement of the contest was that they had to be open source that everyone could see. And then in 2019, we wanted to build on top of that by embracing how well RISC-V works with the security community to have attack-resistant CPU challenge. So there were 5 attack vectors that people needed to build hardware that was resistant to those. And again, they had to be open source FPGA implementations. And I think the 2020 challenge will be announced probably in the summer, but I hope everyone here will be FPGA experts by then and can participate. So one last other cool project that's kind of RISC-V and FPGA. There's a project also out of Berkeley called FireSim. And it is basically a project that makes it easy to run stuff in Amazon's FPGA that are in the cloud. So Amazon has this thing called F1, where you can kind of log in and fire up an FPGA and get your image on it. So it's sort of like there's a badge somewhere in the cloud somewhere that you are talking to, and you're saying, this is what I want to put on that. And then I want it to act like a computer now that I've flashed it with this image. And the thing what it's really trying to do is not necessarily accelerate what you're doing and act like hardware in the most efficient way possible. It's trying to tell you exactly how it's going to work if you actually tape out a chip like this. If you actually build a chip like this that has this sort of memory latency, this sort of networking latency, how well is your data center going to perform if you put 1,000 of these together? So I think it's a really cool project, and it's not necessarily, doesn't really have anything to do with RISC-V, except without RISC-V, they wouldn't have had anything to sort of start with to put on this project. It would have been like, well, let's sit here and see if we can get a license from ARM, or see if we can design our own processor so that we can start. It's like, no, we start with the Rocket Ship repo, and then we work on the cool stuff. So if you want to get involved in RISC-V, the organization has working groups. So when I first joined SiFive, one thing I wanted to do was actually get involved with the RISC-V Foundation. I think I was more excited about that than SiFive. And so when I started, the thing that was sort of on fire was the debug. There was people were saying, we can't use this because we can't debug it. So I worked with the debug task group, and I chaired it for a while. And so we came up with an actual specification for debugging. And now both open source tool like OpenOCD implements the RISC-V debug standard, and as well as tools like Seger and Lauterbach and IAR are also using the RISC-V standard. But there's lots of other working groups. Some of the hot ones right now, I think, are the vector extension task group and the security and crypto extensions task group. There's also groups that are just like in charge of figuring out this compliance question. So that's like a huge value add for the foundation. But if there's anything here that you think sounds cool, or if you have something that you think would be better, like if you got more people involved in talking about it, definitely go to the RISC-V website and see if there's a group about it. And like I said, it's free to join as an individual. You just have to check the whatever membership conditions or something. And finally, I wrote this slide, and then I came here yesterday, and I talked to a lot of people, and I was like, whoa, my information is way out of date. So I had all this stuff that I thought we needed. And so one thing was like, well, we don't have any open source FPGA tools, but like, if you flash this badge, you are just like make, and it like compiles the FPGA image, and that like blew my mind, because that did not exist a few years. So I'm really excited about, I think, Tim's talk tomorrow about SiMaFlow, which is the tool chain that actually does this FPGA that makes it possible to really go top to bottom open source. There's also a problem that I encounter is designing your chip itself with only open source tools. So if you take your sort of logic, like the thing you'll find when you go to look at the repo for this SoC, this FPGA, there's a bunch of code there, and that has to finally get translated down to like little rectangles for the stencil in the factory. And those tools are ridiculously expensive and kind of awful, because nobody uses them because they're expensive, and so they don't have any incentive to make them better because nobody uses them. So I was really excited to hear yesterday about this Open Road project, which is trying to solve that problem in the open source. Come up with a full tool chain from Verilog to GDS. I think there's still a problem for designing an SoC with only open source IPs. So things like DDR5s and Ethernet PHYs and even USB, they are, people design them and they sell them. So they have really no incentive to open source them. I know people, like my old research group at Stanford is working on it's called DragonPhi, so they're working on an open source Phi. But I think there's a ton of work to be done here. And also building your chip in an open source fab. So I don't know, I think right now, like the technologies are getting smaller and smaller and smaller. If we go back in time to the ones that were really big, so like, at some point it's big enough that you could actually make it with like an X-Acto knife and like stuff. I think the hard part is the chemicals, right? So I'm curious to see if anybody can actually come up with an open source fab similar to like a MakerBot type thing. And I know this is a hardware conference, but also software is so important. So if you like porting things, if you like using your RTOSes and operating systems, and you've got different languages like you like to see running, software is really important to kind of help this ecosystem spread. So thank you very much. Let's talk about your projects this week, and I'm really having a great time at this conference.